The simplex algorithm assumes that the initial point is feasible in the primal problem. If b is greater than or equal to 0, then the origin is feasible. If the origin is not feasible, then it is necessary to determine some other initial point that is feasible. It is possible to introduce an auxiliary primal problem specifically designed to help in this task. The process of eliminating artificial variables is performed in phase 1 of the solution, and phase 2 is used to get the optimal solution. Since the solution of LPP is computed in two phases, it is called two-phase simplex method. There is typically a need for elementary row operations to bring the tableau into the form required by the simplex algorithm. Computationally, dual simplex method is same as simplex method. However, their approaches are different from each other. Simplex method initiates with a non-optimal but feasible solution, whereas dual simplex method initiates with a solution that is optimal but infeasible. Simplex method is responsible for maintaining the feasibility while successive iterations are taking place, whereas on the other hand, dual simplex method is responsible for maintaining the optimality. The dual simplex algorithm is most sought after solution method for LPP. Adding newer constraints to a LPP problem customarily leads to the breakup of primal feasibility but not dual feasibility. The dual simplex can be used for frequent re-optimization, barring the requirement of searching solutions of new primal basic feasible. This is of the most use in integer programming, where the use of cutting plane techniques require the introduction of newer constraints at the various stages of the branch and bound, cut or price algorithms. This method helps in the provision of much simplistic ways to the two-phase method for the cases where there is unfeasible starting solution. Dual simplex method can be used where costs which are reduced are positive values, unlike the two-phase method which can always be used. After studying this module, you shall be able to understand the two-phase simplex method, learn dual simplex method, explore the difference between dual simplex and simplex method. We consider the method of two-stage simplex with the example. Minimize x1 plus 2x2 subject to x1 plus x2 greater than equal to 4, x1 minus x2 greater than equal to 1 and minus x1 plus 2x2 greater than equal to minus 1 over x1 greater than 0 and x2 greater than 0, which adding slack variables is equivalent to this first problem. Minimize x1 plus 2x2 subject to x1 plus x2 minus z1 equals to 4, x1 minus x2 minus z2 is equal to 1 and minus x1 plus 2x2 minus z3 equals to minus 1 over x1 greater than or equal to 0, x2 greater than equal to 0, z1 greater than equal to 0, z2 greater than equal to 0, z3 greater than equal to 0. Observe that unlike before, setting x1, x2 equals to 0, 0 does not yield a basic feasible solution. In particular, if x1 equals to x2 which is equal to 0, then z1 equals to minus 4 and z2 equals to minus 1, which are not feasible. So, we need to find a basic feasible solution to start from. The trick is to solve a different optimization problem whose optimal solution is a basic feasible solution for our original problem. For example, we consider the second problem, that is to minimize y1 plus y2 subject to x1 plus x2 minus z1 plus y1 equals to 4, x1 minus x2 minus z2 plus y2 equals to 1, and third, that is minus x1 plus 2x2 minus z3 equals to minus 1 over x1 greater than equal to 0, x2 greater than equal to 0, z1 greater than equal to 0, z2 greater than equal to 0, z3 greater than equal to 0, y1 greater than equal to 0, and y2 greater than equal to 0. We added an extra variable y to each constraint that was negative in our original problem. The positive variable y equals to y1 and y2 tracks the amount we have violated any of our constraints. We then chose to minimize y1 plus y2, which we interpret as the total amount that we have violated our constraints. Note, by adding these extra variables, there is a basic feasible solution with x1 equals to x2, which is equal to 0, where y1, y2, z3 equals to 4, 1, 1. So, we can now solve the second problem using the simplex algorithm. Both problems have the same number of non-zero entries in a basic feasible solution, namely 3. There is a feasible solution to the first problem if the optimal value of the second problem is 0. Thus, once we have solved the second problem, we will be at a basic feasible solution where y1 equals to y2, which is equal to 0. Removing variables y1 and y2, this is then a basic feasible solution to the first problem. All the violated constraints are satisfied and there are the right number of non-zero terms. So, we should solve this problem in two phases. Phase 1. In this phase, the simplex method is applied to a specially constructed auxiliary linear programming problem leading to a final simplex table containing a basic feasible solution to the original problem. Step 1 is to assign a cost 1 to each artificial variable and a cost 0 to all other variables in the objective function. Step 2 is to construct the auxiliary LPP in which the new objective function z star is to be maximized subject to the given set of constraints. Step 3. Solve the auxiliary problem by simplex method until either of the following three possibilities do arise. First, maximize z star less than 0 and at least one artificial vector appear in the optimum basis at a positive level, that is, delta j should be greater than equal to 0. In this case, given problem does not possess any feasible solution. Second, maximize z star equals to 0 and at least one artificial vector appears in the optimum basis at a 0 level. In this case, proceed to phase 2. Third, maximize z star equal to 0 and no one artificial vector appears in the optimum basis. In this case, also proceed to phase 2. So now we can solve this problem using the simplex algorithm in phase 1. Phase 1. Solve the second problem where we added additional variables for violated constraints. As you can see in the table provided, we have written down the simplex tableau for the second problem and added an additional objective row for the objective of the first problem. Notice the simplex tableau is not in the correct form. First, we want z3, y1 and y2 to be the basis elements. So, we need to multiply the third row by -1. Second, the phase 1 objective row contains non-zero entries above basic feasible variables y1, y2. So we need to subtract the first and second rows of the simplex tableau from the bottom objective row. As you can see from the tables, we now proceed to optimize this tableau whilst treating the additional objective row as though it was just an additional constraint. We are now at an optimal solution for the first phase. In particular, we are at a basic feasible solution where x1 equals to 5 by 2 and x2 equals to 3 by 2. We can now remove y1 and y2, the bottom row, and solve the second phase. Phase 2. Now, assign the actual cost to the variables in the objective function and a zero cost to every artificial variable that appears in the basis at the zero level. This new objective function is now maximized by the simplex method subject to the given constraints. Simplex method is enforced to the simplex table, which is modified and acquired at the term of phase 1 until an optimum basic feasible solution has been attained. The artificial variables which are non-basic at the end of phase 1 are removed. Phase 2, that is, removing the additional variables, we have a basic feasible solution for the first problem. We then solve the second problem. So we have now solved our original optimization problem. The optimal solution is x1 equals to 3, x2 equals to 1 with optimal value 5. In the simplex method, row 0 elements would be negative for some till the final iteration when conditions optimality are satisfied. In the case wherein all row 0 elements are non-negative, there is dual feasibility of associated bases. As a matter of fact, if row 0's some elements are negative, dual infeasible basis is achieved. As explained, the primal simplex method is linked with primal feasible. However, dual infeasible basis. The basis is both primal as well as dual feasible at the final optimal solution. Primal feasibility and drive towards dual feasibility is maintained all through the process. Questions for which availability of an initial dual feasible solution is there, dual simplex algorithm are most apt for such kind of problems. Specifically, it is fruitful to re-optimize a problem post the addition of a constraint or post modification of some parameters so as feasibility of previously optimal basis is no longer there. Suppose we are given the LPP problem to minimize z, which is equal to 2x1 plus 3x2 plus 4x3 plus 5x4, subject to the constraints of x1 minus x2 plus x3 minus x4 greater than equal to 10, x1 minus 2x2 plus 3x3 minus 4x4 greater than equal to 6, 3x1 minus 4x2 plus 5x3 minus 6x4 greater than equal to 15, and x1, x2, x3, x4 all greater than equal to 0. Steps involved in the dual simplex method. First step, modification of constraint. All the constraints except those with the equality sign are modified to less than equal to sign. Constraints with greater than equal to sign are multiplied by -1 throughout so that inequality sign gets reversed. Finally, all these constraints are transformed to equality sign by introducing required slack variables. In the above LPP example, if we would have inequalities of less than equal to instead of greater than equal to, then the usual simplex would work nicely. The two-phase method is more tedious. Step 2. Checking modified problem. Modified problem, as in step 1, is expressed in the form of a simplex tableau if all the cost coefficients are positive, that is, optimality condition is satisfied, and one or more basic variable have negative values, that is, non-feasible solution, then dual simplex method is applicable. Considering the LPP example, all coefficients in z equals to 2x1 plus 3x2 plus 4x3 plus 5x4 are non-negative. We are fine for the dual simplex. Selection of exiting variable. The basic variable with the highest negative value is the exiting variable. If there are two candidates for exiting variable, anyone is selected. The row of the selected exiting variable is marked as pivotal row. In the example, we multiply the equations by -1 and add to each of the equations its own variable. Selection of entering variable. Cost coefficients corresponding to all negative elements of the pivotal row are identified. Their ratios are calculated after changing the sign of the elements of pivotal row. That is, ratio equals to cost coefficients divided by -1 into the elements of pivotal row. The column corresponding to the minimum ratio is identified as the pivotal column, and the associated decision variable is the entering variable. After applying selection step to the LPP in the example, we get the following tableau. Pivotal operation. It is similar as in the case of simplex method, considering the pivotal element as the element at the intersection of pivotal row and pivotal column. Now, row 1 on the example LPP is chosen to pivot on. The ratio for x1 is better than for x3, so pivot on A1 1. After pivoting, we get check for optimality. If all the basic variables have non-negative values, then the optimum solution is reached. Otherwise, steps 3 to 5 are repeated until the optimum is reached. After pivoting the problem, every AI 0 for I greater than 0 is non-negative, so the tableau is optimal. But suppose that the boss adds now the new restriction, that is x1 plus 2x2 plus 3x3 minus 4x4 is less than equal to 8. With the dual simplex, we do not need to start from the scratch. We simply add the new row and one more column to our final tableau. Excluding from the last row x1, x6 and x7, we get the tableau. Note that if in the last row there were no -3, then the linear programming problem would be infeasible. Now we pivot on x4, we get the following solution, and this is our final solution. Let us now summarize what we have learned in this module. First, the two phases of simplex method, application of two-phase simplex method, learnt dual simplex method, and found out the difference between dual simplex and simplex method.